Momentum is the fourth major topic in physics after kinematics, forces, and work and energy. Like energy, momentum is easy to measure, but more difficult to verbally define. We will examine the formulas of momentum and the related quantity of impulse, and then examine their significance. Colloquially, we think of momentum as the characteristic of something massive moving at high speed. A jet taking off on a runway has a lot of momentum. By contrast, a snowflake doesn't seem to have much momentum, even if it's in the middle of a blizzard. And an object at rest would have no momentum. So, by this visualization, momentum involves two characteristics: mass and velocity. Momentum is symbolized by the lowercase letter p. It is calculated according to this equation. Momentum equals mass times velocity. Momentum is measured in kilogram meters per second. There is no shorthand for this set of units. Now, let's compare this to kinetic energy. Kinetic energy also involves mass and velocity, and the equations look pretty similar, but there are major differences. In kinetic energy, velocity is squared, and that turns kinetic energy into a scalar. In momentum, velocity is not squared, so it stays a vector. Unlike kinetic energy, momentum is a vector. It has direction. All those I hats and j hats that were unnecessary in energy come rushing back in momentum. Moreover, we know that since kinetic energy is the product of mass, which must be positive, and the square of velocity, which must also be positive, kinetic energy itself must also be positive. But that's not true for momentum. Since momentum doesn't square velocity, the velocity can be negative, and so momentum can also be negative. Here we see a moving soccer ball. Clearly, it must have momentum. Let's calculate how much it has. What is the momentum of a 2 kilogram ball traveling at 6 meters per second rightward? In this question, we have a soccer ball which is initially moving rightwards at 6 meters per second. I am going to set my origin at the ball, and I'm going to set the rightward direction as being the positive direction. Now, the momentum of the ball would be calculated as follows. Momentum is equal to mass times velocity, which is equal to a mass of 2 kilograms times a velocity of 6 I hat meters per second. That works out to 12 I hat kilograms from the mass times meters per second from the velocity. So the initial, or the momentum of the ball is 12 I hat kilogram meters per second. In this visualization, the ball initially moves rightward, so the momentum is pointed rightward. But the goalie deflects the ball and causes it to move leftward. After the collision, the momentum is also leftward. The momentum has changed. A change in momentum is called impulse. It is symbolized by the letter J. It is calculated like this. Take a photo of an object at some point and calculate its momentum. Then take a photo at a later point and calculate its new momentum. The final momentum minus the initial momentum is the impulse. Impulse is a vector measured in kilogram meters per second. Now, the momentum of the ball changed because the velocity of the ball changed. But a change in velocity is an acceleration, and accelerations are caused by unbalanced forces. In this case, the force that the goalie exerts on the ball. There's a close link between impulse and force, and it can be expressed mathematically. For my 101 students, in addition to being the final momentum minus the initial momentum, impulse also equals the average force on an object multiplied by time. My 103 students would express the same equation a bit differently using calculus. Impulse equals the integral of force with respect to time. These two statements mean comparable things. Let's use impulse in practice. A 2 kilogram soccer ball is traveling at 6 meters per second rightwards. A goalie intercepts the ball and sends it moving leftward at 1 meter per second. The ball was in contact with the goalie for 0.05 seconds. What force did the goalie apply to the ball? In the second part of this question, the goalie stops the ball and deflects it so that it starts traveling at 1 meter per second leftwards. So if we can think of the initial motion of the ball as being what we solved for earlier, that would be photo 1. And the leftward motion of the ball after the goalie deflects it would be photo 2. The momentum over here would be given as, again, mv2, which works out to 2 kilograms, multiplied by, in this case, the ball is moving at 1, but it's leftward, so that would be -1 I hat meters per second. All of which works out to -2 I hat kilogram meters per second. So that is the final momentum of this ball. Now the next thing to do is to find out how big the impulse is. Impulse, symbolized by the letter J, is calculated as final momentum minus initial momentum, which is equal to -2 I hat minus 12 I hat, which is -14 I hat kilogram meters per second. Finally, since we were told that the time required for the collision was 0.05 seconds, and since the impulse is also equal to average force multiplied by time, that means that -14 I hat is equal to average force, which is what we have to calculate, times a time of 0.05 seconds. -14 divided by 0.05 gives us -280 newtons. So that means that the average force that the goalie exerted on the ball in order to reverse its direction was -280 I hat newtons. Now, let's explore momentum and impulse in 2 dimensions. We'll use our familiar I hat and J hat notation, using techniques similar to what we did in 2D kinematics. Consider this puzzle. A 0.1 kilogram hockey puck is traveling east at 2 meters per second. A hockey player applies a force of 10 newtons pointed south. The final velocity of the puck is 2 meters per second eastwards and 20 meters per second southwards. How long did the puck feel a force from the player? Initially, we have a puck that is moving eastwards. But later on, a force appears which causes the puck to move eastwards but also southwards. this direction, and this direction. We were told that the initial velocity, first of all, was 2, and that the final velocity still maintains that 2 in the horizontal direction, but we now have an additional component of 20, or more correctly, negative 20 in the vertical direction. We could set up some axes like this. I'm going to set northwards as being positive y and rightwards as being positive x. We were also told that the mass of the puck is 0.1. I'm going to consider this photo 1, and I'm going to consider this photo 2. So in photo 1, the momentum of the puck is equal to mass times velocity, which is equal to mass, 0.1 kilograms, times a velocity of 2 meters per second, which works out to 0.2 I hat, this velocity was of course an I hat, kilogram meters over second. In photo 2, the momentum is still equal to mass times velocity, which works out to 0.1 kilograms multiplied by 2 I hat minus 20 j hat. And all of that comes to 0.1 times 2 would be 0.2 I hat. 0.1 times 20 gives us negative 2 j hat. So the impulse over here is equal to P2 minus P1, the difference of the two momenta. That's 0.2 I hat minus 2 j hat minus 0.2 I hat. And all of that is going to work out to 0.2 minus 0.2 is 0. That works out to negative 2 j hat. Now, we were told that the force being exerted was negative 10 j hat newtons, and we were being asked to find the time. Impulse is equal to average force, this was the average force, multiplied by time. So that would be negative 2 j hat. By the way, the units for impulse are the same as the units for momentum, kilogram meters per second, is equal to the average force, which was negative 10 j hat newtons, multiplied by the time. Divide both sides by negative 10, and you end up with the time of the collision being 0.2 seconds. So now we have found out that in order to produce this change in momentum, given the fact that you exert a force of negative 10 j hat newtons, apply a force in this direction, downwards, the time that was required was 0.2 seconds. We can also solve momentum questions where the impulse is at an oblique angle. In these cases, we have to break the impulse into its x and y components, very similar to what we did in kinematics and forces. Consider this puzzle. A 0.3 kilogram baseball is traveling west at 5 meters per second. A baseball player hits the ball. The bat contacts the ball for 0.05 seconds. It hits the ball with 200 newtons of force at an angle of 30 degrees above the eastward x-axis. What is the final velocity of the ball? In this question, we have a 0.3 kilogram baseball, which is initially traveling leftward at 5 meters per second, but it feels a force and subsequently starts traveling in the opposite direction. The force, of course, comes from the bat. So I can't draw the bat, but you can imagine there being a collision over here and the ball gets sent off in this direction. Let us apply some axes to this. Before we go any further, I will say that this is going to be photo 1 before the collision with the bat takes place, and this is going to be photo 2, which is after the collision with the bat takes place. I'm going to set rightwards as being positive and upwards as being positive. Now, let us write down what information we know. The size of the force is 200 newtons. The angle of the force was 30 degrees above the horizontal. So we can take this force, which is currently given to us in polar form, that is a size and an angle, and we can break it into its two components. This is the opposite side of this right triangle. So that means that the vertical component is going to be given by the force 200 newtons times the sine of 30 degrees. I happen to know that when you solve this out, you're going to get 100 newtons. The sine of 30 is 0.5. This horizontal component is the adjacent side to this angle. So that means that this is going to be given by F cos 30 degrees. So this opposite side was F sine 30 degrees. This adjacent side is F cos 30 degrees, which is 200 cos 30 degrees, which works out to 173.2. Now that we have all of this information, we can solve for what the initial momentum of the ball was, and we can solve for the impulse that the ball experienced, because we were told that the time required for the collision was 0.05 seconds. So the initial momentum is mass times velocity, which is mass 0.3 kilograms, velocity -5 I hat meters per second. -5 because it's moving in the negative x direction. Multiplying all of that out, we get -1.5 I hat kilograms meters over seconds. Now, what is the impulse that the ball experienced? Well, impulse is equal to force multiplied by time, which works out to a force of, I will write this down as being 173.2 I hat newtons plus 100 J hat newtons, multiplied by a time of 0.05 seconds. And you'll notice that what I've done is I have written this force in rectangular coordinates. So even though we were given in polar, that's 200 newtons at 30 degrees, we translated it into rectangular, that's 173 in the horizontal direction and 100 in the vertical direction, and we will use this for our calculation to make things simpler. So 173.2 multiplied by 0.05 gives us 8.66 I hat plus 100 times 0.05 gives us 5 j hat. And the units would be newtons times seconds, which is also equal to kilograms times meters over second. Now, the last step, now that we have solved for how big the impulse is impulse is also equal to P2 minus P1. So, an impulse of 8.66 I hat plus 5 j hat is equal to P2 minus P1, which was negative 1.5 I hat. So, if we were to just add, if we were to simplify this expression, which I shall do over here, we would have 8.66 I hat plus 5 j hat equals P2 plus 1.5 I hat. We can add this I hat term to both sides, add the 1.5 I hat to both sides, like this. That would cancel it from here, and we would now have 10.16 I hat plus 5 j hat is equal to the momentum in the second photo. So, last step. The momentum in the second photo is equal to the mass times the velocity. And we already know that the mass is 0.3 kilograms. So we now just need to divide everything by 0.3 in order to find out what that final velocity is. So the final velocity is equal to 10.16 I hat plus 5 j hat, all divided by 0.3. which works out to 10.16 divided by 0.3 gives us 33.87. Plus 5 divided by 0.3, which gives us 16.66. And since it's a velocity, this is measured in meters per second. So we have now solved for the final velocity of this baseball. Let's go through this process once again. We started by taking a force vector which was given to us in polar and converting it into rectangular. We solved for the initial momentum, we solved for the impulse using force times time, but impulse is also equal to the change in momentum. It's equal to P2 minus P1. Therefore, since we know the impulse, we just solved for that, that must be equal to P2 minus P1, and then with basically a bit of arithmetic, we solve for P2. Finally, since P2 is equal to mass times velocity 2, we just need to divide both sides by the mass, 0.3, and we can solve for what the final velocity of the ball is immediately after the collision. You might be wondering what the point of momentum is. Let's look at this game of billiards. The cue ball is about to collide with the other balls. We'll take a photo before the collision occurs. We can measure the masses and velocities of the balls before the collision. We can calculate the momentum of each ball individually and add them up to find the total momentum before the collision. The symbol for total momentum is this. That accordion-shaped letter at the left is the capital Greek letter sigma, which means total. Now, let's let the collision play out. Again, we can measure the velocities of the balls and therefore their momenta. What we find is the total momentum of the balls just before the collision always equals the total momentum of the balls just after the collision. This sounds profound, and it looks like we're in for another conservation law. But there's a catch. Here, a ball bounces on the ground. At first, its velocity is clearly downwards, so its momentum must also be downwards. But after the bounce, the velocity and the momentum are both upward. The momentum changed because the ball felt a force and therefore an impulse from the ground. There's an exception to the law of conservation of momentum. It doesn't apply if the objects under examination feel an outside force. If the objects we're examining collide with each other, then momentum will be conserved. But if they feel an outside force, an outside impulse, then momentum is not conserved. The reason we consider the force from the ground to be an outside force is because we weren't considering the motion of the Earth when the ball bounced off of it. If we had measured the momentum of the Earth before and after the collision, we would have found that the combined momenta of the Earth and the ball were conserved. So to sum up, the total momentum of objects before a collision equals the total momentum of the objects after the collision unless they feel an outside force. This is the law of conservation of momentum. The law of conservation of momentum is a universal law, just as important as conservation of energy. In the following videos, we will see examples of how to use this powerful law.